Dr. Ranjani Partha-Sarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. So, we have been looking at the cache organization. So, we have looked at direct mapped cache and we looked at associative cache, both fully associative cache and set associative cache. So, we will look at certain considerations with respect to performance of these caches. That is what we will look at in today's class. So, when we talk of performance, there are these three terms that we normally refer to: hit time, miss rate and miss penalty. So, recollect these three terms. Hit time is the time that it takes to access a particular data in the cache, assuming that it is available in the cache. Miss rate is the number of accesses when it is not there in the cache. So, that is a miss. The miss rate is the number of times that you have a miss. Miss penalty is the time taken when there is a miss to access the data from memory and bring it into the cache. So, whenever you have a miss, there is extra time that is taken to access the data from the memory. So, your average memory access time therefore is dependent on your hit time, the miss rate and the miss penalty. Okay. So, we have already seen that the average memory access time will be equal to hit time plus miss rate into miss penalty. All these three factors are important for us. Okay. So, now with respect to the three caches, that is direct mapped cache, set associative and fully associative caches, we need to understand how these three factors are affected, that is hit time, miss rate and miss penalty. How is it that they vary with respect to these three different organizations? So, in general you will see that miss rates are lower in the associative caches. So, this is something that we saw because you will have a little more flexibility in terms of where it can go in the associative cache. We have already seen that in a direct mapped cache, if there are two accesses mapping on to the same location, they will keep replacing each other. So, you will have more number of misses in that case. But when you have some associativity, even if it is a two-way or a four-way set associative cache, you will still be able to get that flexibility and therefore, it will reduce the miss rate. So, that is one thing that you can look at. But there is another thing to understand with respect to the miss rates. The misses also depend on the memory access patterns and the program behavior. That is depending on, for instance, let us say your with respect to the instruction cache as well as with respect to the data cache. Program behavior, that is whether you have a loop that is being executed a number of times, okay, depending on the temporal locality and so on, the memory access will differ and that again can cause different miss rates. Similarly, with respect to data access, depending on how the data is being accessed, whether it is a continuous set of data being accessed, for instance, a complete array being accessed and so on, there is a lot of spatial locality in the data being accessed. So, memory access patterns also will affect the miss rates. Okay. So, in general it is very important to understand how these misses behave. In fact, when you talk about studying cache performance, people study a lot of memory access patterns and what kind of things give rise to these different misses and so on. And they also look at the impact of the size of the cache, number of blocks that are there in the cache and also look at how many, what is the size of each block in the cache and the types of associativity or the degree of associativity that you can have. All these are different parameters with respect to which you can study the performance of the cache. So, all these are important. Okay. So, let us first start with understanding misses. Now, let us look at how this misses will affect your overall performance of the CPU. Okay. So, you can see that when the CPU performance increases, that is you have your entire system consisting of your processor and your memory subsystem. So, let us look at these two as two subsystems. So, if I improve the performance of my CPU, now we have already seen that there are different ways in which you can improve the CPU performance. That is your CPI, the clock cycles per instruction is reducing, for a base CPI is reducing, let us say. So, when the base CPI reduces, the effect of your misses becomes even more significant. That is, if your miss penalty is high, it will affect your CPU performance a lot more, especially when the CPU performance has increased quite a bit. That is, let us say my original CPI was 3 and I reduced my CPI to 1 by using certain CPU related techniques. Now, for the same CPI now, if I am compared to CPI of 3, if you have a CPI of 1, okay, the miss penalty will become more significant. Okay. So, that is something to keep in mind. So, your memory subsystem performance should normally match your CPU performance, which is very difficult to attain, but we always try to match that. Second thing of course is, when the base CPI decreases, a greater portion of the time is spent on the memory stalls. So, again important to look at the miss penalty and so on. Third is when you have an increasing clock rate, okay, because we know that we increase clock rate in order to improve your CPU performance. So, if you increase the clock rate, what will happen is again memory stalls will take more number of CPU cycles. Therefore, again your overall CPI will increase, okay, that is also to be kept in mind. So, whichever way we try to improve CPU performance, if your memory performance does not match it, right, you will always find that there is a negative effect in terms of the overall performance. So, point that we have to therefore note is that you can't neglect the cache behavior when you are evaluating the overall system performance, and to understand the cache behavior we need to understand how the system behaves with respect to the different misses and so on. So, let us look at the different misses. Okay. Normally what we say is we can classify the misses in terms of how these misses occur or where they originate from. Okay. So, we talk about the 3 C's with respect to misses. So, the source of misses is what we try to understand. Where are they originating from? Okay. The first type of misses are called as compulsory misses, or they are also referred to as cold start misses. That is, when you start a program, okay, when or the first access to a block, it is in memory, obviously it will not be there in your cache. So, it has to be brought from memory to cache. So, the first access to a block is always going to cause a cache miss. Okay. So, these are referred to as compulsory misses. This is the first type of miss that we look at. Second type of miss that we look at is what is called as a capacity miss. Now, what is a capacity miss? This occurs because you only have a finite amount of size for your cache. Okay. So, due to the finite cache size, because always the cache size will be much smaller than the main memory size, for the reason that a cache size is much more expensive. So, you can't afford to have very large caches, it will become very expensive. So, we have a limited cache size, and because the cache size is limited, when you bring in new blocks into the memory, it will have to replace something which is there in the cache. That refers to what is called as a capacity miss. Okay. So, it can also happen because a replaced block is again accessed. You just replaced a block, and again if you access it, that is again going to come back into the cache. Okay. So, that will cause a capacity miss. So, compulsory miss is one, capacity miss is the second type of miss. The third type of miss is what we call as the conflict miss, or it is also referred to as a collision miss sometimes. So, what do you mean by conflict miss? This happens when two different blocks in memory will map to the same block in the cache. Okay. So, this typically happens in a non-fully associative cache. In a fully associative cache, you can't say it is a conflict miss, because it is not necessarily that it has to be placed only in that particular position. Okay. Whereas, in a direct mapped cache, conflict misses will be much higher. Okay. Why would it be higher? Because we know that a particular block will only come into a particular position in the cache. Therefore, you will have conflict misses. Whereas, in a fully associative cache, you do not have to worry about conflict misses, because it is not going to exactly come into the same position. It is more of a capacity miss that we need to worry about. Whereas, in a set associative cache, which is in between these two, so it has to come into a particular set that is determined. So, if you have a set which is already full and another block is coming in which has to come into that particular set only, then that would be a conflict miss, because it has to come into that particular position only. Okay. Even if there is some other position which is free, it can't go in there, right, because it has to come only into this position. So, that refers to a conflict miss. So, you can see that conflict miss will not occur in a fully associative cache of the same total size, but in a set associative cache, due to competition for entries in a set, it will occur, and in a direct mapped cache, because it has to come only into a particular position, definitely it will occur. Okay. So, we understand misses, therefore, we in fact study the misses with respect to compulsory misses, capacity misses and conflict misses. And again you can see that the compulsory misses, capacity misses and conflict misses will also depend on size of the cache, size of the block size, and will also depend on the cache organization. It will also depend on the type of program that you have, that is the program behavior and the memory access pattern that is available in that particular program. So, what works well for a particular program may not work the same way for another program. Okay. So, program behavior could change, that is something that can happen. So, when we look at the different design trade offs that we have, so we can look at the effect of all these three, that is changing the cache size, increasing the associativity and increasing the block size, and see what is its effect on the miss rate and so on. Okay. So, look at this. When we increase the cache size, which of these three misses, that is compulsory miss, capacity miss or conflict miss, will it reduce? Okay. So, if you look at that, when we increase the cache size, you will find that the capacity misses will decrease. That is natural, right, because you increase the cache size, capacity is increased, therefore, capacity misses will naturally decrease. Okay. This is something that you have. But will it have any negative performance effect? That is, by increasing the cache size, am I likely to have a negative performance effect? It may increase the access time. So, that is something that one needs to worry about. So, this is a design option we have, which will have an effect on the miss rate, it will decrease the miss rate, but it could increase the access time. This is one design aspect that we need to consider. Second is increasing the associativity. So, this we know, increasing the associativity will definitely decrease the conflict misses that you have. It will decrease the conflict misses. But again, what is the negative performance effect that it is likely to have? This again may increase the access time. Why will it increase the access time? Because when your associativity is increased, more number of comparisons to be done simultaneously, and then that has to be passed through a multiplexer in order to get the required block in the cache. So, it may increase the access time. Okay. Of course, if you have a very efficient implementation of that comparator, it may not increase the access time, but in general increasing associativity may increase access time, but it will decrease your conflict misses for you. The third is option that we have is increasing the block size in the cache, that is each block, the size of each block is increased. Now, which of these three misses is it likely to decrease? If you look at it, will decrease the compulsory misses. Why will it decrease compulsory misses? Because remember, what is a compulsory miss? It is the first access to a block. Okay. Now, when I increase the block size, okay, what happens? Let us say I am increasing the block size from 4 to 8. Okay. So, what does it mean? It means that when I get a first miss for a block, I am going to now bring in 8 different words into memory, okay, as opposed to bringing in 4 different words from memory into the cache. Now, I am bringing in 8 words from the memory into the cache. So, if it was a sequence of access that is taking place, now the other, I have already brought one, already accessed one particular word in the cache, the next 7 accesses to the cache will result in a hit. Okay. Whereas, if my block size was 4, the next 3 accesses would have resulted in a hit, but when I come to the 5th axis, the 5th axis now will result in a miss because it is not there in my block. So, when I increase my block size, I am bringing in more words of the same block into the cache, and so if those are the words which are being accessed consecutively, naturally my compulsory misses will decrease. Okay. So, increasing block size therefore has the effect of decreasing the compulsory misses. So, we actually have one mechanism by which we can try to decrease each of these different misses, capacity miss, conflict miss and the compulsory miss. Okay. But what is the negative effect of increasing the block size? Increasing the block size will increase the miss penalty. Now, why will that happen? Why will it increase the miss penalty? Because when a miss occurs, we have to bring a block from the memory into the cache, and if the size of the block is larger, naturally it will take more time for you to bring it from memory to the cache. Reading 4 bytes from memory or reading 8 bytes from memory, naturally 8 bytes will take more time. Therefore, when you have a miss for a larger block size, okay, you will have higher miss penalty. Okay. So, this is something that we need to keep in mind. Okay. So, we will take a short break and then come and continue. Welcome back after the break. So, we were just looking at the 3 different types of cache misses, the capacity miss, conflict miss and the compulsory misses, the 3 C's as they are referred to. And we saw how increasing cache size or increasing associativity or increasing block size can help to reduce one of these misses. So, this is something that we have seen. Next thing we will look at is the effect of memory access patterns on the misses. Okay. That is, how does cache interact with the software? Different programs have different behavior, different algorithms have different behavior. Okay. So, how is it that the how these things affect the cache miss patterns? Okay. So, in fact, number of studies have been done on this. Okay. So, what people have done is that they have looked at different algorithms and seen how the cache behavior could vary. Okay. For instance, if you take a simple sort program, you have different sorting algorithms. For instance, this picture just gives you a study with respect to two different sort algorithms, radix sort and a quick sort. Okay. So, we will look at just the cache misses that you get per item. It is found that the number of items to sort increases, number of cache misses that you have per item, okay, is less for a quick sort, whereas it varies differently for a radix sort. Okay. So, you can find, I mean, this picture is basically to show that you can have different behavior depending on the algorithm that you choose, okay, because it will lead to different memory access patterns, and because it leads to different memory access patterns, you will have different types of misses. Okay. So, in fact, one of the things that is normally done is you have compiler optimizations for memory access, that is, the compiler will try to see that it is ordering the memory access in a particular manner, so that the number of misses are reduced. So, these are other options that people look at in terms of improving cache performance. So, this is one other aspect to remember. Okay. Another thing that we look at when we look at improving cache performances, okay, so far we looked at misses and decreasing the miss rate. Now, another aspect of course is our miss penalty, which is the time taken to access the main memory whenever you have a miss. So, how do I reduce my miss penalty? So, reducing miss penalty basically means I should improve my memory access time. So, how do I improve my memory access time, especially when my block sizes are larger? Okay, this is another aspect that we need to look at. So, how can main memory organization support caches? That is the next thing we need to understand. So, what do we normally do? We normally use DRAMs for main memory. So, we already seen what dynamic RAMs are. Okay. It is a fixed width that you would have, okay, that is being accessed from the main memory. And normally what happens is the DRAM is connected to your processor and your cache subsystem by means of a fixed width clocked bus. Okay. And normally the bus clock is slower than the CPU clock, and because of this it takes a longer time for your access to take place. Okay. So, how do we improve the performance given these constraints? So, let us look at typically how much time it would take. Okay. So, let us say we have a 4-word block, okay, and a 1-word wide DRAM, which means I will have to access 4 different words from the DRAM. So, let us look at let us take an example to understand how the bus cycles affect our overall memory access time. Okay, let us take this example where it takes 1 bus cycle for address transfer, 15 bus cycles for per DRAM access, and 1 bus cycle per data transfer. Okay. So, we need to first give the address and then access the data, right, and then transfer the data. So, this is what we are looking at. So, if this is the system that we are looking at, right, these are the number of clock cycles that we are looking at. Now, let us see for a 4-word block and a 1-word wide DRAM, what will be the miss penalty? So, what is the miss penalty? First, I need to put out the address, which takes 1 bus cycle, plus now 4 words have to be accessed. We said that 15 bus cycles per DRAM access. So, you will have 4 into 15, 60 cycles for the accessing the data, and then we said it takes 1 bus cycle per data transfer. Now, there are 4 words being transferred. So, 4 into 1. So, 1 plus 4 into 15 plus 4 into 1, totally it will take 65 bus cycles. Okay, this will be my miss penalty. This is how we would calculate our miss penalty. Now, what is the bandwidth, okay, memory bandwidth that we talk about? So, that is we are trying to find out how many bytes are transferred in how many clock cycles. So, how many bytes did we transfer here? We said 4-word block, okay. So, let us say it is 16 bytes that are being transferred, okay. So, 16 bytes divided by how many clock cycles? 65 cycles. So, approximately about 0.25 bytes per cycle, that is the bandwidth that you get. Okay. So, this is the kind of bandwidth that your main memory, this particular memory organization will be able to support. So, the question therefore is, how do I increase this memory bandwidth? Okay. So, to increase the memory bandwidth, we look at different memory organizations. Okay. You can look at a 1-word wide memory organization, which is what we saw just now, or we can go in for a wider memory organization. Okay. So, 1-word wide memory organization would be like this: processor, cache, the bus is as broad as 1 word, which is how broad your memory also is. Okay. So, you just transfer 1 word at a time, right, through the bus into the cache. So, the other option that we have that we can look at is a word wide memory organization. Okay. So, if you say for instance, this is the cache block is 4-word wide, okay, I am putting my memory also to be 4-word wide, my bus is also 4-word wide. So, which means I can do this transfer in 1 clock cycle itself. That is, remember in this example, it took us 4 into 15 to access and 4 into 1 to transfer. So, that is what I am now trying to reduce. Okay. So, what I therefore do is I will be able to access, because my memory itself is organized as 4 words, right. So, in one axis 4 words will be accessed together. So, it will take just 15 clock cycle, it is only one axis, okay, but in one axis I will access 4 words. So, 1 clock cycle to put out the address, 15 clock cycles to access the data, plus 1 clock cycle to transfer the data. Okay. So, 1 plus 15 plus 1, which comes to 17 bus cycles. So, what is happening now? What happens to the bandwidth now? 16 bytes are accessed in 17 cycles. So, I get a bandwidth of 0.94 bytes per cycle, much better bandwidth. So, naturally your miss penalty will decrease. Okay. So, this is what we do. So, increasing the bus bandwidth. But what is the negative side of this? Naturally, increasing the bus bandwidth, increasing the bus size, these are expensive options. So, it is a trade off that we have to look for. Okay. That is what we look at. Okay. So, can I do something where without increasing this bus size, okay, because I know that is an expensive option. Can I do something so that I can still have a higher bandwidth, okay, and get this performance benefit that I am looking for. Okay. It turns out that there are some interesting memory organizations that are used for this purpose. One such memory organization is what we refer to as a interleaved memory organization. Okay. So, what we do in this case of an interleaved memory organization is this: the memory that you have, okay, we do not look at it as a wide memory as such, but you look at it as memory divided into different banks. We talk about a bank 0, bank 1, bank 2, bank 3. Okay. So, in this example, for instance, I have divided my entire memory into 4 banks, and each bank, okay, will have one word of the block that I am looking for. So, if I look at a particular block of memory, that block is spread out across these memory banks. So, word 0 of a particular block is here, word 1 will be in bank 1, word 2 will be in bank 2, and word 3 will be in bank 3. Okay. So, what I do therefore is, when I need to access a particular block, I start the access in all the 4 banks simultaneously. So, I will start the access simultaneously. So, which means in 15 clock cycles the word is available for me from each of these banks, and then in every subsequent clock cycle I can transfer one word out of this memory. Okay. So, what am I achieving here? My total miss penalty now will be 1 clock cycle to transfer the address, and then 15 clock cycles to access all the 4. The 4 will take place simultaneously. Okay. And then the transfer of the data from the banks to the cache has to take place 1 per clock cycle. So, it will take me 4 into 1, okay, clock cycles. So, it will take 1 plus 15, 16 plus 4, 20 bus cycles. Okay. So, 20 bus cycles for the miss penalty. So, what is my bandwidth then? 16 bytes are being transferred in 20 cycles. So, I get a bandwidth of 0.8 bytes per cycle. You can see that it is much better than our single word, not as good as our word wide organization, but you are getting it at the with the benefit that your bus is no longer very big. So, the cost of the bus and this organization is less. Okay. And memory also, you are not going for any special memory, same memory, only thing is that it is organized in terms of the banks, in terms of banks. Okay. And we call it as interleaved because address 0 will be here, address 1 will be here, address 2 will be here, address 3 will be here, and then 4 will be here, 5 will be here, 6 will be here, 7 will be here, and so on. Okay. So, we call that as an interleaved memory organization, and with this kind of a memory organization you can get a better performance. Okay. So, this is something that we do from the memory side in order to improve your performance. So, reduce miss penalty and increase the bandwidth by doing these kind of operations. Okay. Other things that we do is we try to support advanced DRAM organization itself. How can my DRAM itself be organized such that you are able to support a better memory access? So, what has been happening in the DRAM arena is that we have mechanisms by which you are able to support DRAM accesses of an entire row. Instead of saying that only one word is accessed at a time, entire row can be accessed in a time. So, we also have support for burst mode access, wherein you can supply successive words from a row with reduced latency. So, these are things that are normally supported in DRAMs today. We also have what are called as double data rate DRAMs. So, wherein you are able to transfer data faster. Okay. So, you transfer data both on the rising edge of the clock and the falling edge of the clock. So, which is called as a double data rate. Your data rate is doubled because you are transferring 2 words during one clock, and that is a double data RAM. You also have what are called as quad data rate RAMs, where you will have separate DDR inputs and outputs, by which you are able to increase the data rate by 4 times. So, that's why it is called as a quad data rate RAM. So, these are some DRAM organizations that are available, which help us to improve our memory access time as such and reduce the miss penalty. Okay, so, these are some operations that we have. Yet another improvement that we have in terms of improving cache performance, okay, is what is referred to as a multi-level cache. So, now so far we talked about one cache and one memory. So, cache is very fast, memory is very slow, and we looked at how to kind of find a something in between these two. So, another option is not just have one level of cache, but have more than one level of cache. So, you can have a L1 cache, which is the lowest level, and then you have an L2 cache and an L3 cache, and then the main memory. So, typically what we do is L1 cache is fastest, L2 cache will be slightly slower than that, L3 cache will be slightly slower than that, and then you will have the main memory. So, if you have 3 levels of caches, so what you do is, if it is not there in L1 cache, now you look in the L2 cache. If it is not there in the L2 cache, then you look in the L3 cache. Not there in the L3 cache, you look in the main memory. Because your L2 and L3 caches are slower than your L1 cache, they will also be cheaper. Okay. So, it is basically a cost performance trade off that you are looking at. Okay. So, idea is have a very fast L1 cache, very expensive, no problem, but it is small. L2 cache slightly bigger than that, but it is slower and less cost. L3 cache again slower, less cost than L2, okay, but it will be larger in size. So, by using a proper combination of these different types of caches, different sizes of caches and different speeds of cache, which are at these different levels, we can try to get better performance. Okay, that is what we do in multi-level caches. So, in fact, if you look at today's processors, you have these kind of multi-level caches that are used. So, a quick look at what we have, the kind of performance benefits you can have when you use a multi-level cache. Okay. So, if you look at, for instance, a base CPI of 1, clock rate is 4 gigahertz, miss rate per instruction 2%, and main memory access time is 100 nanoseconds. With just the primary cache, your miss penalty will be 100 nanoseconds with a 4 gigahertz. Okay. So, per 0.25 nanoseconds, therefore, it will give you 400 clock cycles that it will take. That will be your miss penalty. So, effective CPI will become 1 plus 0.02, which is your miss instruction rate, into 400 cycles, 9. This is with just the primary cache. Now, let us say we add an L2 cache here. L2 cache, let us say, has an access time of 5 nanoseconds, and the global miss rate to main memory is 0.5%. So, what I mean by global miss rate to memory, that is the access that actually go to main memory. Okay. Now, primary miss with L2 hit, okay, that is not there in L1, but it is there in L2, that I get a hit in L2, then what will be my penalty? It is there in L2, right. So, 5 nanoseconds is all that it will take. So, how many clock cycles? 5 nanoseconds divided by 0.25 nanoseconds. So, 20 cycles extra if it is there in L2. If it is not there in L2, that is I get an L2 miss, only then I go into my main memory. In that case, what we do is we get an extra penalty of 500 cycles. So, your effective CPI becomes 1 plus 0.02 into 20 plus 0.005 into 400, which is 3.4. So, the performance benefit you get will be 9 by 3.4, which is 2.6. So, you can see the performance benefit you get by using this kind of a 2-level cache. So, this is something that is done. Okay. So, to summarize, what we have looked at in today's lecture are the following. We have looked at performance considerations, we have looked at understanding misses, the 3 C's as we say of the cache: capacity miss, compulsory miss, and the conflict misses. We also looked at how we can reduce miss penalty by using main memory support, and we also looked at the use of multi-level caches. Okay. Questions to go over the material today. Question number 1, what are the 3 C's with respect to caches? Question number 2, which of the 3 C's cannot be reduced? Question number 3, how can the average memory access time be reduced? Question number 4, how does a multi-level cache help? Thank you.